Welcome to tonight's journey into the deep sea. Please close your eyes and breathe very slowly. Allow your daily stress to fade away entirely. The noisy world above is quietly going to sleep. We are leaving the chaotic surface far behind us. Our deep submersible vessel is ready for a descent. Listen to the gentle hum of the submarine engines. The cabin is dimly lit with soft red lights. You are completely safe inside this reinforced pressure sphere. Let the rhythmic sound of the sonar calm you. Your breathing syncs with the slow descent of the vessel. We are leaving the atmosphere of Earth entirely behind. The surface world feels like a distant, fading dream. Down here, time seems to slow to a tonight. We travel to the vast, dark Indian Ocean. Specifically, we seek the Central Indian Ridge hydrothermal system. This is a place of profound, silent geological mystery. The Indian Ocean covers huge stretches of our planet. It is a boundless expanse of dark, heavy seawater. This ocean is bounded by massive continental landmasses above. We navigate toward the southern hemisphere of the globe. Our target lies near 23 degrees south latitude. The precise longitude is roughly 69 degrees east entirely. This remote area sits east of the island Madagascar. It rests far below the busy commercial shipping lanes. Surface waters here remain warm throughout the entire year. Monsoon winds frequently churn the ocean waves far above. Fierce cyclones sometimes sweep across this specific location holds a deep, ancient geological secret. Scientists officially call this area the Kairai hydrothermal field. Another nearby site is named the Edmund Vent Field. Japanese marine researchers discovered Kairai in the year 2000. The field was named after their advanced research vessel. The word Kairai translates directly to ocean ridge in Japanese. This name perfectly describes its remote, submerged geological location. Scientists like Dr. Ken Takai studied these exact coordinates. They sought hidden microbial life in the darkest oceanic depths. Dr. Takai theorized this environment could support ancient life forms. He proposed that early Earth resembled this exact environment. The fluid the Central Indian Ridge is a massive underwater scar. It divides the ocean floor into distinct geological sections. This region represents a divergent tectonic plate boundary zone. Two massive pieces of Earth are slowly pulling apart. The giant African plate steadily moves to the far west. The Indo-Australian plate drifts slowly toward the distant east. They separate at a speed of mere millimeters yearly. This slow divergence literally tears the solid ocean crust open. Molten magma rises from the deep mantle far below. The liquid rock fills the expanding tectonic gap continuously. It cools instantly upon touching the frigid, deep seawater. New oceanic crust is constantly born in this total darkness. This continuous process shapes the entire global ocean floor. Nearby lies the famous Rodriguez Triple Junction geological area. Three massive tectonic plates meet at earthquakes frequently rattle this submerged mountain range system. Human ears cannot hear these deep, low seismic rumbles. The shifting rocks create deep faults, fissures, and cracks. Cold seawater seeps down into these newly formed chasms. The ocean water penetrates kilometers deep into the crust. It reaches the hot magma chambers hidden far below. This creates a highly complex underground thermal plumbing system. The ridge crest features a deep central rift valley. This rift valley is several kilometers wide in some places. Steep fault scarps form the towering walls of this valley. The valley floor is paved with recent lava eruptions. Volcanic activity here is entirely hidden from human eyes. Heat flows outward from the Earth's molten liquid core. It steadily warms the rocks of the lower. Our digital depth gauge displays steadily increasing numeric values. We slowly sink past the 1,000-meter depth mark. Sunlight cannot penetrate this deep into the ocean water. The water outside our thick window turns completely pitch black. We drop through the twilight zone of the mesopelagic. Faint traces of blue light vanish completely from our view. Bioluminescent creatures occasionally flash in the dark, cold water. They use chemical lights to hunt or find rare mates. We leave these glowing deep-sea animals far above us. Our descent takes us into the bathypelagic ocean zone. This zone extends down to 4,000 meters deep. The water here is incredibly still and deeply silent. Suspended particles drift lazily in the weak ocean currents. We are officially entering the midnight zone of Earth. Our final destination is much further down. The Kyray field rests at 2,400 meters deep. The Edmund field sits deeper at 3,300 meters. Let us settle near the 2,500 meter mark. This depth equals exactly 2.5 kilometers down. Falling to this extreme depth takes several quiet hours. The water temperature drops steadily as we slowly descend. Surface warmth fades into a near-freezing, permanent chill. Ambient water here is just 2 degrees Celsius now. This bitter cold is constant throughout the entire year. Seasons simply do not exist in this abyssal marine realm. Ocean currents here move with incredible, sluggish deliberation constantly. Antarctic bottom water creeps slowly along the ocean floor. The physical weight of the ocean is truly immense. Above us sits a massive column of dense seawater. Every 10 meters adds another atmosphere of hydrostatic pressure. At this depth, the pressure is incredibly staggering. It measures roughly 250 atmospheres total. This equals 25 megapascals of constant, crushing downward force. Human bodies could never survive this harsh, extreme environment. Our titanium submarine safely protects us from the heavy weight. The thick metal hull groans softly under the immense strain. Water density increases slightly in these extreme physical conditions. Such pressure fundamentally changes the physical properties of water. Boiling points rise dramatically in the deep sea environment. Water here can reach over 400 degrees Celsius. It remains strictly liquid despite the extreme thermal energy. This supercritical fluid behaves in fascinating and strange ways. It dissolves heavy metals directly from the surrounding rocks. Hydrostatic pressure is a relentless, invisible. We activate our powerful exterior halogen lights right now. A narrow beam pierces the eternal, heavy oceanic darkness. Marine snow drifts slowly past our thick acrylic viewports. These tiny organic particles fall continuously from the surface. They look like glowing fairy dust in our bright headlights. The seafloor slowly comes into our limited visual range. We see a rugged landscape made entirely of volcanic rock. Fresh basalt flows form dark, twisted, bulbous pillow shapes. The cold seawater quenches the erupting lava almost instantly. This rapid cooling forms a shiny glassy rind on the rocks. Obsidian-like glass shards litter the newly formed ocean floor. Older rocks are lightly dusted with pale, soft marine sediments. Steep ridges rise like underwater mountain peaks nearby us. Deep valleys cut through the fractured, brittle oceanic crust. These transform faults run perfectly perpendicular to the main ridge. There is no soft sand mineral deposit stain the gray rocks with vibrant color. Iron oxides create striking patches of deep rusty red. Sulfur compounds leave bright streaks of pale, vivid yellow. We glide silently over this completely alien geological landscape. The sonar pings softly inside our quiet, dark cabin. It maps the unseen topography lying just ahead of us. A vast hydrothermal vent field approaches our small vessel. Heat shimmers clearly in the cold water just below. The ocean floor is literally breathing in the dark. There is absolutely no sunlight to support plant life. Photosynthesis is completely impossible in this pitch-black, deep realm. Yet, this barren rock hides a thriving biological oasis. The secret lies in the geothermal heat radiating from below. Seawater seeps through microscopic cracks in the basaltic crust continually. It travels downward for perhaps 2 or 3 solid kilometers. The water approaches the shallow. The immense pressure prevents this water from actually boiling. It becomes a highly reactive, buoyant supercritical fluid mixture. This fluid strips chemical elements from the surrounding hot rocks. It absorbs high amounts of sulfur, iron, and heavy copper. Magnesium is entirely removed from the seawater during this heating. The chemical composition of the fluid changes completely underground. This toxic, acidic mixture then rises rapidly back upward. It seeks the path of least resistance to the surface. It shoots out of the seafloor through focused volcanic vents. Upon hitting the freezing ocean, the dissolved minerals instantly precipitate. They form dark clouds of solid, microscopic metallic particles. These particles slowly build the towering hydrothermal chimney structures. The Chi-ray field sits on a rocky, uneven slope. The Edmond field is located roughly 160 kilometers away. Edmond is situated slightly further south along the mid-ocean ridge. It rests at a much deeper depth of 3,300 meters. Both fields host incredibly active, high-temperature black smoker chimneys. These chimneys spew dark, mineral-rich fluids into the ocean continuously. The surrounding water is stained black by the falling sulfides. Our vessel hovers gently above this alien, submerged landscape. The thrusters hum quietly as we maintain our steady position. We are completely isolated from the rest of the world. This deep oceanic trench feels like another planet entirely. The pressure outside remains a constant, deadly physical threat. Yet inside our cabin, we remain warm, safe, and calm. The observation cameras are recording every single detail outside. Scientists back on the surface will study this footage later. For now, we alone bear witness to this hidden world. The towering chimneys cast long, eerie shadows across the rock. These mineral spires look like an abandoned, ruined underwater city. We drift slowly past a particularly tall, smoking vent structure. The black fluid billows upward like smoke from a fire. It disperses slowly into the surrounding cold ocean water currents. This delicate balance of heat and cold is truly mesmerizing. It lulls the mind into a state of deep relaxation. You can feel the heavy, peaceful weight of the ocean. It wraps around our vessel like a thick, protective blanket. There is nothing to worry about in this quiet place. The deep sea demands nothing from you but peaceful observation. The story of the Indian Ocean vents begins with a fascinating scientific puzzle. For decades, the deep waters here remained a complete and absolute mystery. Researchers had already found thriving hydrothermal systems in the vast Pacific Ocean. The Atlantic Ocean had also revealed its deep and hidden thermal secrets. However, the expansive Indian Ocean represented a massive blank space for oceanographers. Marine biologists constantly wondered if life existed in these remote, dark depths. Geologists wanted to understand the underlying tectonic activity of this specific region. The central Indian Ridge separates the African plate from the Indo-Australian plate. This massive geological boundary spreads apart. Early clues emerged during initial expeditions in the late 20th century. Oceanographers detected subtle chemical anomalies drifting within the deep water column. Traces of dissolved iron hinted at hidden geological processes occurring far below. Elevated levels of methane strongly suggested active venting on the ocean seafloor. Helium isotopes provided the final definitive proof of deep magmatic influence. These unique chemical signatures formed invisible plumes drifting silently through the darkness. Researchers, the real breakthrough finally happened in the pivotal year of 2000. A highly dedicated expedition set sail to find these completely elusive vents. The Japanese research vessel Kairai navigated slowly into the designated target zone. This impressive ship carried highly advanced deep-sea exploration and mapping technology. A team of international scientists gathered aboard this specialized floating laboratory. Chief Scientist Jun Hashimoto led the ambitious and dedicated marine biology team. Toshitoka Gamo directed the incredibly complex chemical analysis of the ocean water. They focused their combined efforts on the rugged central Indian Ridge. The specific target area lay thousands of miles from any known coastline. Surface conditions were often quite. The crew deployed a deep-tow camera system to scan the dark bottom. This sensitive instrument hovered just above the jagged and newly formed basaltic crust. Sensors continuously measured the surrounding water temperature and its overall optical clarity. The temperature graph suddenly spiked sharply on the control room monitoring screens. Light transmission dropped as the sensors encountered thick suspended particulate matter. These crucial readings confirmed they were directly above an active hydrothermal site. The team immediately prepared to launch the remotely operated vehicle named Kaiko. The Kaiko submarine was a true marvel. Of heavy hydraulic cranes lifted the bright yellow submarine off the wooden deck. The robotic vehicle slipped beneath the surface and began its long descent. Skilled operators guided the machine through the sunlit upper layers of water. The surrounding ocean slowly turned into a profound and absolute pitch black. Kaiko steadily descended past the impressive 1,000-meter depth mark. The ambient pressure increased by 1 atmosphere every 10 meters of descent. At 2,000 meters, the surrounding water temperature hovered very near freezing. The entire descent took several hours of careful and incredibly precise piloting. Finally, the downward-facing altimeter detected the rapidly. The vehicle successfully arrived at a depth of 2,450 meters. The exact geographical coordinates were 25 degrees 19 minutes south latitude. The precise longitude was recorded as 70 degrees 2 minutes east. High-definition video feeds transmitted the very first images back to the ship. The scientists watched the glowing screens in quiet, deeply focused anticipation. Shimmering water suddenly appeared against the cold background of the deep ocean. Massive sulfide mineral chimneys rose majestically from the volcanic ocean floor. Dark, mineral-rich fluid billowed rapidly from the tops. This momentous event marked the very first vent found in the Indian Ocean. Temperature probes slowly extended from the mechanical robotic arms of the vehicle. The digital readings showed the vent fluid reaching 360 degrees Celsius. This extreme heat was constantly sustained by shallow magma chambers located below. The immense pressure of surrounding seawater prevented the superheated fluid from boiling. The remarkable discovery of the Kyre field changed marine biology forever. It provided a crucial missing link in global hydrothermal vent ecosystem research. Scientists had previously debated how vent organisms dispersed across vast ocean basins. The Indian Ocean sits directly between the Atlantic and the Pacific Oceans. Finding deep-sea life here offered vital clues to ancient biological migration pathways. The expedition collected extensive. The massive success of the Kyre expedition inspired immediate follow-up scientific missions. A second major hydrothermal discovery occurred just one single year later. In 2001, an American research team arrived in this region. They sailed aboard the advanced research vessel named the Thomas G. Thompson. Scientist Cindy Lee Van Dover led this highly anticipated subsequent biological expedition. They utilized the remotely operated vehicle Jason for their deep underwater dives. This particular team explored a completely different segment of the central Indian Ridge. They moved further north along the actively spreading. The Jason vehicle descended into a much deeper section of the ridge. It carefully navigated through steep rocky canyons and massive geological fault lines. The seafloor topography here was incredibly complex and potentially quite treacherous. They eventually reached a staggering depth of 3,300 meters. The exact coordinates read 23 degrees 52 minutes south latitude. The precise longitude was recorded at 69 degrees 35 minutes east. Here, they found the second major Indian Ocean hydrothermal vent system. This spectacular new site was officially named the Edmund Hydrothermal. The Edmund field presented a slightly different geological environment than the Kyre site. It was situated on a noticeably older section of the oceanic crust. The hydrothermal chimneys found here were significantly taller and much more fragile. Some impressive sulfide structures reached towering heights of over 30 meters. The venting fluids at the Edmund site were also incredibly hot. Thermometers recorded maximum fluid temperatures of 380 degrees Celsius. The specific fluid chemistry differed slightly from the southern Kyre vent site. Edmund fluids contained much higher concentrations of certain. The discovery of Edmund definitively proved that Kyre was not an anomaly. The central Indian Ridge clearly hosted a widespread and active hydrothermal network. These two discoveries fundamentally altered our understanding of deep-sea global biogeography. The Indian Ocean vent sites revealed a truly unique biological community. It contained a strange and fascinating mixture of Atlantic and Pacific species. Some organisms shared direct genetic ties with Western Pacific vent fauna. Other deep-sea creatures strongly resembled those found on the mid-Atlantic ridge. This genetic evidence confirmed the Indian Ocean as an evolutionary biological crossroads. The expeditions brought back thousands of high-resolution digital photographs of the seafloor. These detailed images allowed scientists. The renowned research vessel NOAA also visited this remote region later on. It deployed the autonomous underwater vehicle ABE for highly detailed sonar surveys. The ABE submarine flew in tight grid patterns over the rugged terrain. It generated highly accurate bathymetric maps of the complex vent structures. These precise maps revealed the exact alignment of the tall sulfide chimneys. The towering chimneys clustered along specific tectonic faults in the ocean crust. This alignment showed how deep geological fractures control hydrothermal fluid flow. The early 2000s became a true golden age for this region. Multiple nations sent their very best research ships to the Indian Ocean. The German research vessel Sun conducted extensive geological mapping operations here. Chinese scientific expeditions later discovered the initial discovery by the Kairai team remains a deeply historic milestone. It required immense patience and incredibly precise navigation to finally succeed. Finding a vent field is exactly like finding a needle in a haystack. The ocean is incredibly vast, and the specific target is unbelievably small. The scientists relied on invisible chemical trails to guide them through darkness. They trusted their sensitive instruments over thousands of meters of deep water. The successful deployment of KAICO validated many years of intense engineering effort. Deep-sea exploration demands perfect coordination between the ship and the robotic vehicle. The tether connecting KAICO to Kairai relayed vital telemetry and video data. This long fiber optic cable carried the heavy burden of modern scientific discovery. The exact moment the subsequent Edmund discovery further cemented the global importance of this ridge. Van Dover and her scientific team worked tirelessly during their entire expedition. They operated the Jason ROV in grueling and exhausting 12-hour shifts. Processing the biological samples required meticulous and constant attention to detail. The deep-sea creatures had to be preserved immediately upon their surface recovery. Sudden changes in pressure and temperature could easily ruin the delicate specimens. The shipboard laboratories constantly buzzed with quiet, deeply focused scientific activity. Geochemists carefully titrated water samples to measure the dissolved hydrogen sulfide. Microbiologists cultured heat-loving bacteria in highly specialized and pressurized incubators. Every single piece of data contributed to a massive multidisciplinary scientific study. The remarkable findings were eventually published in prestigious international science journals. These academic papers described the highly unique tectonic setting of the ridge. They comprehensively detailed the specific mineralogy of the Kairai massive sulfide ores. Zinc and copper form the primary structural matrix of the Kairai vent field, sits near the famous Rodriguez triple junction. This is the exact place where three major tectonic plates slowly drift apart. The complex stress field creates deep geological pathways for seawater penetration. Extremely cold water sinks down through deep cracks in the ocean floor. It travels several kilometers deep into the intensely hot basaltic crust. The water rapidly heats up and reacts chemically with the surrounding rocks. It becomes highly buoyant and rises rapidly back toward the ocean surface. This continuous and powerful cycle powers the deep-sea hydrothermal fluid engines. The discovery of these engines in the Indian Ocean was absolutely monumental. It successfully completed the global map of deep-sea hydrothermal vent distribution. It definitively proved that active venting occurs in every major ocean basin. The pioneering work of these early expeditions will never be forgotten. The names deep beneath the Indian Ocean lies a massive geological seam. The central Indian ridge separates two giant tectonic plates. The African plate slowly drifts away from the Indo-Australian plate. This divergent boundary stretches for thousands of submerged kilometers. Farther south, a complex geological feature anchors the system. The Rodriguez Triple Junction connects three distinct oceanic ridges. Here, the Antarctic plate joins the slow tectonic movements. Massive forces pull the oceanic crust apart in three directions. This continuous separation creates deep fissures in the dark seafloor. Magma from the Earth's mantle rises to fill these voids. The rising magma cools instantly in the freezing bottom water. This process forms scientists classify the central Indian Ridge as an intermediate spreading center. The massive tectonic plates separate at about 45 mm per year. This rate falls below the fast-spreading East Pacific rise. It is significantly faster than the slow-spreading Mid-Atlantic Ridge. Intermediate spreading rates create unique geological structures on the seafloor. The deep magma supply here is neither constant nor completely absent. Periods of intense volcanic activity alternate with quiet tectonic stretching. Deep detachment faults form during the quiet periods of stretching. These massive faults expose deep mantle rocks to the ocean. The seafloor topography reflects this intermediate and steady spreading rhythm. Steep rift valleys alternate with smoother, volcano-covered axial highs. This varied gravity pulls the cold seawater kilometers down into the crust. The water descends through a complex network of microscopic cracks. Deep beneath the seafloor, the fluid approaches the magma chamber. Intense geothermal heat warms the descending seawater to extreme temperatures. The temperature gradient near the magma chamber is incredibly steep. Pressures at this depth prevent the superheated water from boiling. The fluid reaches temperatures exceeding 400 degrees Celsius. At these temperatures, the seawater undergoes a profound chemical transformation. The heated fluid loses all its dissolved oxygen and magnesium. It becomes highly acidic and chemically aggressive towards surrounding rocks. This corrosive fluid leaches heavy metals from the oceanic crust. Iron. In the year 2000, researchers made a crucial discovery. Japanese scientists aboard the research vessel Kairai explored this ridge. They deployed the remotely operated vehicle Kaiko into the depths. Lead scientist Toshitoka Gamo directed the underwater geological exploration mission. The research team located the hidden Kairai hydrothermal vent field. This field sits at 25 degrees 19 minutes south latitude. The precise longitude is exactly 70 degrees 2 minutes east. These hydrothermal vents rest at a depth of 2,450 meters. The Kairai field rests on a typical basaltic rock foundation. However, the vent fluids exhibit highly unusual and rare chemical signatures. The hydrothermal fluids' further oceanic investigations revealed the source of this hydrogen gas. Beneath the basaltic surface lies a dense layer of ultramafic rock. Deep mantle peridotite was exposed by ancient tectonic faulting events. The heated seawater interacts directly with this iron-rich peridotite layer. This interaction triggers a chemical reaction known as geological serpentinization. Serpentinization alters the olivine minerals within the deep mantle peridotite. This natural alteration process produces massive amounts of hydrogen gas. The resulting hydrothermal fluids are completely unique to this region. Scientist Junichiro Ishiboshi analyzed these fluid samples in the laboratory. He measured fluid temperatures reaching 365 degrees Celsius. The fluid chemistry directly another major hydrothermal site exists further north along the ridge. The Edmund Vent Field was discovered 1 year after Kairai. Marine geologist Cindy Lee Vandover participated in this expedition. The Edmund Field is located at 23 degrees 52 minutes south. Its exact longitude coordinates are 69 degrees 35 minutes east. This active vent system sits much deeper than the Chi-ray field. The dark seafloor here drops to 3,300 meters. A remotely operated vehicle named Jason mapped the Edmund Field. The geological setting here differs slightly from its southern neighbor. The Edmund vents are situated on the wall of a rift valley. Massive tectonic forces uplifted the Edmund Field rests entirely upon typical mid-ocean ridge basalt. The fluids venting here are exceptionally rich in dissolved heavy metals. Scientists recorded fluid temperatures of 380 degrees Celsius. The extreme oceanic depth prevents the fluid from boiling upon exit. However, phase separation occurs deep within the crustal plumbing system. Subsea floor boiling creates two distinct types of hot hydrothermal fluids. A dense, high-salinity brine sinks lower into the oceanic crust. A lighter, vapor-rich fluid rises quickly toward the dark ocean floor. The Edmund vents discharge this vapor-rich, low-salinity hydrothermal fluid phase. High concentrations of dissolved chlorine characterize this specific fluid type. The fluid chemistry: when the superheated fluid meets the cold ocean, minerals precipitate. The ambient seawater maintains a steady temperature of 2 degrees Celsius. The sudden thermal shock forces dissolved metals out of the solution. Black clouds of metallic sulfides billow into the dark bottom water. These particles slowly settle to build massive underwater mineral chimneys. The chimney formation process follows a very specific chemical sequence. Calcium sulfate, known as anhydrite, forms the initial chimney framework. Anhydrite only precipitates at temperatures above 150 degrees. This fragile white mineral creates a temporary and highly porous shell. The superheated fluid continues flowing through this porous anhydrite tube. The inner walls, the chalcopyrite, forms a dense, golden layer inside the active chimney. This inner lining insulates the rising fluid from the cold seawater. The outer walls of the chimney consist of completely different minerals. Zinc sulfide, known as sphalerite, dominates the middle chimney layers. Iron disulfide, or pyrite, forms the outermost protective mineral crust. This concentric mineral zonation tells a story of shifting thermal gradients. The chimney walls grow thicker and structurally more stable over time. Some mineral structures at the Chi-ray field reach truly massive proportions. Towering sulfide spires grow up to 30 meters tall here. These massive structures are incredibly heavy and inherently physically unstable. Tectonic tremors: frequently geologists use radiometric dating to determine the age of these fields. They analyze the decay of specific radioactive isotopes within the minerals. Radium-226 and Li-210 provide highly accurate geological timelines. The central Indian Ridge itself formed over 50 million years ago. However, the individual hydrothermal vent fields are geologically much younger. The Chi-ray vent field has been active for several thousand years. Mineral deposits suggest periods of dormancy followed by intense renewed activity. The Edmund Field shows a similar chronological pattern of hydrothermal venting. Magmatic intrusions periodically reignite the hydrothermal circulation deep underground. An active vent chimney might only live for a few short decades. The underlying hydrothermal system: recent scientific expeditions have mapped even more vent fields in this region. The Pelagia vent field was discovered further south along the active ridge. German scientists utilized the autonomous underwater vehicle Abyss for this mapping. The Pelagia field sits exactly at 39 degrees south latitude. This site exhibits a completely different style of deep hydrothermal venting. It is a lower temperature system driven entirely by slow tectonic cooling. The clear vent fluids here barely reach 100 degrees Celsius. White smoker chimneys completely dominate the landscape at the Pelagia field. These chimneys lack the dark metallic sulfides of the much hotter vents. They are composed primarily of pure white silica and dense barium sulfate. The silica precipitates slowly. The heavy deposition of silica signifies a maturing and cooling hydrothermal system. As the underlying magma chamber cools, exiting fluid temperatures slowly drop. The dissolved metals precipitate deep below the seafloor in the fractured crust. Only the highly soluble silica remains in the slowly ascending hydrothermal fluid. The silica eventually coats the older sulfide chimneys in a thick glaze. This glassy coating preserves the extinct chimneys from rapid destructive ocean erosion. Extinct chimney mounds constantly dot the flanks of the central Indian Ridge. They serve as silent, towering monuments to ancient and powerful hydrothermal activity. Geologists map these extinct massive sulfide deposits using advanced acoustic sonar. These ancient deposits contain vast chemical records of past global ocean chemistry. They reveal how the central Indian Ridge represents a pristine deep geological laboratory. The complex interaction between tectonic spreading and magmatic heat is perfectly balanced. This balance sustains the deep hydrothermal circulation over many thousands of years. The intermediate spreading rate creates the ideal structural permeability for fluid flow. Deep faults allow cold seawater to reach the superheated and fractured lower crust. Magmatic intrusions provide the necessary and constant thermal energy for the system. The unique presence of exposed mantle peridotite adds incredible deep chemical complexity. The resulting vent fluids carry massive amounts of newly dissolved deep minerals. These minerals build the towering chimneys that define the strange seafloor landscape. The constant precipitation of sulfides creates rich and valuable metallic ore deposits. Every tiny earthquake and the geological formation of these vents is a steady process. It connects the deep mantle to the freezing ocean above. The African and Indo-Australian plates continue their silent separation. New magma will eventually rise to heal the fractured crust. The Kyray and Edmund fields will one day go extinct. Their towering chimneys will slowly crumble into the ocean mud. New hydrothermal vents will inevitably form along active fault lines. The endless cycle of crustal creation and venting will persist. The central Indian Ridge will continue its steady outward expansion. The deep ocean floor remains a dynamic and ever-changing frontier. The rocks and minerals. Our journey continues along the central Indian Ridge. The ocean floor here is fractured and restless. Tectonic plates slowly pull apart in the darkness. This geological separation creates deep fissures in the crust. Cold seawater seeps down into these dark abyssal cracks. Magma chambers heat the water deep beneath the seafloor. The superheated fluid eventually rushes back upward under pressure. It bursts through the crust to form hydrothermal vents. We are observing the physical architecture of these systems. Towering mineral structures rise from the barren basalt plains. These formations are the Kyray vent field contains many of these structures. This specific field sits at a depth of 2,450 meters. Tremendous ocean pressure keeps the boiling water entirely liquid. Without this pressure, the fluid would instantly become steam. Instead, it remains a dense and mineral-rich chemical soup. The fluid temperature often exceeds 350 degrees Celsius. We can see thick black smoke billowing into the smoke is actually a jet of dark metallic particles. Dissolved minerals precipitate instantly upon hitting the freezing seawater. The surrounding ocean water is merely 2 degrees Celsius. This extreme temperature gradient forces minerals out of solution. Iron and sulfur combine to form tiny dark particulates. These iron sulfide particles give the plume its dark color. Slowly, these falling particles build the physical chimney walls. A chimney grows upward layer by microscopic mineral layer. Some of these structures grow incredibly fast over time. A black smoker can grow 30 centimeters in one day. Many chimneys at the Kyrre field reach massive heights. The Edmund vent field sits slightly further south. It is located near 23 degrees south latitude. The depth at the Edmund field reaches 3,300 meters. Chimneys in this region display slightly different structural characteristics. They often form wide mounds rather than slender spires. The base of a typical mound spans 30 meters across. The internal plumbing of a black smoker is highly complex. A central channel carries the fastest and hottest fluid. Temperatures inside this main conduit reach 380 degrees Celsius. The inner walls are lined with shiny chalcopyrite crystals. Chalcopyrite is a golden mineral composed of copper-iron sulfide. Moving outward, the chimney wall becomes much more porous. The middle layers consist primarily of zinc-rich sphalerite. The outermost crust interacts directly with the freezing ocean. This outer shell is composed of crumbly anhydrite and pyrite. Anhydrite is a calcium sulfate mineral dissolving in cold water. It only remains solid. The chemical composition of the vent fluid is fascinating. It contains extremely high concentrations of dissolved hydrogen sulfide. Methane and hydrogen gases are also abundant in the flow. Magnesium is notably absent from the hot vent fluid. The surrounding rock absorbs all magnesium during the heating process. In return, the fluid extracts heavy metals from the basalt. This chemical exchange alters the oceanic. We also find white smokers scattered across the Indian Ocean. White smokers emit a pale and milky hydrothermal fluid. These specific structures operate at significantly lower temperature ranges. The fluid inside a white smoker averages 250 degrees Celsius. They lack the dark iron sulfides found in black smokers. Instead, their plumes contain high amounts of barium and calcium. Silica is also a major component of white smoker fluid. The chimneys themselves are often lighter in physical color. They appear pale gray or sometimes starkly bright white. White smokers usually form on the periphery of the main field. The fluid moves much slower through these peripheral structures. It seeps gently rather than blasting forcefully into the water. Scientists have studied these Indian Ocean structures extensively. The Japanese submersible Shinkai 6500 visited the Kyrre field. This historic dive occurred during the year 2000. Researchers carefully measured the precise temperature of the venting fluid. They recorded a maximum temperature of 365 degrees Celsius. The remotely operated vehicle Kaiko also mapped this deep terrain. High-definition cameras captured the intricate details of the chimney walls. Later expeditions brought the ROV Jason to the Edmund field. Dr. Cindy Van Dover analyzed the mineral samples collected here. Her team documented the unique geochemical signatures of the region. The central Indian Ridge fluid is unusually rich in hydrogen. This high hydrogen content fuels unique microbial ecosystems. The physical environment is incredibly harsh and highly dynamic. Vent chimneys are inherently unstable and prone to frequent collapse. A 20-meter tower might suddenly snap under its own weight. Earthquakes along the ridge frequently topple these brittle mineral structures. When a chimney falls, the hot fluid continues to flow. It simply begins building a brand new structure immediately. The seafloor is littered with the debris of fallen chimneys. These massive mounds of sulfide rubble slowly oxidize over time. They turn a dusty rust color in the dark ocean. Geologist Ken Takai led several important surveys of this rubble. He studied the subsea floor fluid deep beneath the vent. Fluid temperatures exceed 400 degrees Celsius. We call this subterranean region the hydrothermal reaction zone. Here, seawater becomes a highly corrosive and acidic solvent. The pH of the venting fluid is typically around 3.4. This makes it roughly as acidic as concentrated grapefruit juice. The acid easily dissolves solid rock deep within the crust. The resulting fluid is completely devoid of the physical shape of each chimney tells a unique story. Some vents look like thin needles piercing the black water. Others resemble massive beehives leaking dark fluid from every pore. Flanges are another common structure found on these large mounds. A flange is a flat mineral shelf jutting outward horizontally. Hot fluid gets trapped underneath these overhanging mineral ledges. It forms shimmering inverted pools of superheated water. The trapped water slowly percolates upward through the porous shelf. Minerals precipitate on top, thickening the flange over time. These shimmering pools are a mesmerizing sight in the deep. The refractive index of we carefully pilot our cameras closer to the active flow. The acoustic sensors pick up a low, continuous rumbling sound. This noise is generated by the violent expulsion of fluid. The flow rate from a black smoker is surprisingly high. Fluid exits the main orifice at 2 meters per second. This constant upward thrust prevents the chimney from clogging immediately. However, minerals inevitably build up inside the narrow central channel. The conduit slowly constricts as chalcopyrite crystals grow inward. Eventually, the internal passage may become completely blocked with minerals. The pressurized fluid will then force a new path outward. It bursts through the side wall to create a new spire. The total heat output of this field is truly staggering. Scientists estimate the Kyray field releases hundreds of megawatts. This geothermal energy dissipates slowly into the surrounding deep ocean. The Edmond field produces a similarly massive thermal signature. Ocean currents sweep the hydrothermal plumes far from their source. The dark smoke rises hundreds of meters above the seafloor. It eventually reaches a level of neutral buoyancy in the water. The plume then spreads horizontally across the Indian Ocean basin. These chemical clouds can be detected many kilometers away. Research vessels use chemical sensors to hunt for these plumes. A device called a CTD rosette is lowered into the water. It measures conductivity, temperature, and depth in the water column. Anomalies. The discovery opened a new chapter in deep ocean geology. Prior to this, the Indian Ocean was largely unexplored. Most hydrothermal research had focused on the Pacific and Atlantic. The central Indian Ridge proved to be geochemically unique. The underlying mantle rocks here are unusually close to the surface. This proximity influences the specific metallic makeup of the chimneys. We observe high concentrations of rare earth elements in the crust. Gold and silver are also found in microscopic trace amounts. These precious metals are locked within the solid sulfide matrix. The quiet darkness of the deep sea surrounds these violent structures. There is a peaceful rhythm to the continuous flow of fluid. The vents have been active here for thousands of years. They represent the breathing mechanisms of our living planet. Heat from the Earth's core finds its release. The Solitaire Field is another fascinating Indian Ocean site. It sits at a depth of 2,600 meters. Solitaire features a massive central chimney named the Lone Star. This solitary structure vents clear fluid at 300 degrees Celsius. The clear fluid indicates a lower concentration of dissolved metals. Instead of black smoke, it creates a shimmering thermal wave. We call these transparent emissions diffuse hydrothermal flows. Diffuse flow often surrounds the base of larger black smokers. It gently warms the basalt rocks to a comfortable temperature. The mineral textures here are incredibly varied and visually striking. Some chimney surfaces are the Pelagia vent field offers yet another structural variation. It is located further north along the central Indian Ridge. Chimneys at Pelagia exhibit an unusually high zinc content. Their outer walls have a distinctively pale grayish hue. The fluid here is slightly cooler, averaging 320 degrees Celsius. Deep ocean currents slowly erode these fragile mineral towers. The constant flow of seawater smooths their rough outer edges. Over millennia, entirely new vent fields will form nearby. The old chimneys will crumble into lifeless piles of rubble. This cycle of birth, and we watch the dark smoke rising endlessly into the void. The steady rumbling of the earth lulls the ocean to sleep. It is a mesmerizing display of raw planetary energy. The Indian Ocean hides these wonders perfectly in the dark. We drift slowly past the towering monuments of sulfide. The warm glow of the submersible lights fades into the hydrothermal fluid. Chemistry reveals a hidden deep ocean world. Research vessels gather vast data from the central Indian Ridge. The Japanese submersible Shinkai 6500 collected pristine deep water samples. These liquid samples originated from the Kairai hydrothermal vent field. The Kairai field sits near 25 degrees south latitude. Its exact longitude is 70 degrees east in the ocean. The sampling depth measures exactly 2,400 meters. Scientists measured the fluid temperature at 360 degrees. This extreme deep heat alters the fundamental chemistry of seawater. Cold ocean water penetrates deep into the fractured oceanic crust. Geothermal heat forces the heated water back toward the seafloor. This journey strips heavy minerals from the surrounding basaltic rocks. The resulting fluid carries a highly unique chemical signature. The measured pH levels of these vents present harsh environments. Surrounding deep ocean water maintains a mild pH of 7.8. Hydrothermal fluids emerge with a highly acidic chemical pH profile. The Kairai vent fluids show an end-member pH of 3.2. This high acidity results from deep subsurface rock chemical reactions. Magnesium drops out of the seawater during extreme crustal heating. This magnesium removal process generates massive amounts of hydrogen ions. These free protons drive the pH levels drastically downward constantly. The Edmund vent field sits further north on the ridge. Fluids from Edmund display a slightly different pH of 3.3. This slight variation indicates different fluid residence times deep below. Researchers compare this extreme acidity to the mid-Atlantic ridge. The famous Lost City field features highly alkaline vent fluids. Lost City vents boast a pH ranging from 9. Salinity in these hydrothermal fluids fluctuates through deep phase separation. Deep crustal temperatures occasionally exceed the critical point of seawater. Pressurized seawater boils violently deep within the fractured rock channels. This boiling process separates the fluid into two distinct phases. One phase becomes a dense brine rich in dissolved salts. The other phase forms a low salinity vapor carrying gases. The Edmund vent field emits hot fluids with low chlorinity. Chloride concentrations measure roughly 380 millimoles per kilogram. Normal ocean seawater contains about 540 chloride millimoles. This depleted salinity indicates a vapor phase fluid venting system. The Chi-ray field exhibits slightly elevated chloride levels instead today. Its vent fluids measure 560 millimoles per kilogram. This measurement suggests the presence of a heavier brine phase. Such subtle variations make the Indian Ocean vents. Hydrogen sulfide represents a crucial component of local vent chemistry. This dissolved gas provides vital energy for chemosynthetic microbial life. The Chi-ray field vents emit massive quantities of hydrogen sulfide. Concentrations reach roughly 15 millimoles per kilogram of hydrothermal fluid. This chemical concentration is highly toxic to most marine life. Deep-sea organisms have evolved to utilize this toxic gas. The Edmund field shows slightly lower dissolved hydrogen sulfide levels. Edmund vent fluids contain about 10 millimoles per fluid kilogram. Researchers compare these toxic chemical values to the East Pacific rise. East Pacific rise vents often show lower overall sulfide concentrations. The elevated sulfide in the Indian Ocean supports unique ecosystems. Dr. Ken Takai analyzed the sulfur isotopes within these fluids. His research revealed complex subsurface microbial sulfur reduction processes occurring. Isotope ratios indicate a mixture of magmatic and seawater methane concentrations at the Chi-ray field puzzle many deep oceanographers. These vents release unusually high amounts of dissolved methane gas. Dissolved methane levels reach 2.5 millimoles per kilogram. This concentration significantly exceeds typical basaltic ocean vent gas emissions. Most mid-ocean ridge vents emit far less methane gas. The high methane points to a geological process called serpentinization. Ultramafic rocks from the deep mantle interact with hot sea water. The mineral olivine alters into a softer mineral called serpentine. This rock hydration reaction releases vast quantities of hydrogen gas. The hydrogen then reacts with carbon dioxide in the crust. This abiotic synthesis produces methane without any biological input whatsoever. The Chi-ray field sits near the central Indian Ridge megamullion. This huge geological feature exposes deep mantle rocks to the dissolved metals dominate the visible chemistry of the vent plumes. Iron concentrations reach roughly 2.5 millimoles per kilogram. Manganese levels hover around 1.5 millimoles per kilogram. These transition metals remain dissolved in the hot acidic fluid. They precipitate instantly upon contacting the cold oxygenated ocean seawater. This rapid chemical precipitation forms the iconic black smoker chimneys. Fine microscopic particles of iron sulfide create the billowing smoke. The East Pacific rise generally produces much higher iron concentrations. Indian Ocean vents feature a highly unique zinc to iron ratio. Zinc concentrations measure around 40 micromoles per kilogram right here. Copper levels reach roughly 15 micromoles per kilogram of fluid. These specific metal ratios dictate the local mineral deposit composition. Chimneys grow rapidly as these dissolved metals solidify constantly. Carbon dioxide acts as the primary carbon source for microbes. Dissolved carbon dioxide levels reach 12 millimoles per kilogram here. This abundant dissolved carbon fuels the base of the food web. Helium isotopes provide clues about deep mantle gas degassing processes. Scientists measure the exact ratio of helium-3 to helium-4. The Chi-ray field shows a very distinct primordial helium signature. Helium-3 originates directly from the deep Earth's lower mantle. Its presence indicates a direct geological pathway to the interior. The measured ratio is 8 times the atmospheric background level. This high ratio matches observations from the East Pacific rise. It confirms active magmatic input driving the deep hydrothermal circulation. Dissolved silica concentrations offer another window into the deep subsurface. Silica levels measure around 18 millimoles per kilogram of fluid. Geochemists use dissolved silica as a reliable deep trace. Chemical elements provide further details about the crustal composition. Lead concentrations measure merely 50 nanomoles per kilogram of fluid. Cadmium levels sit around 20 nanomoles per kilogram of fluid. Despite their low abundance, these elements shape the microbial environment. Rare earth elements display a characteristic chondritic mineral distribution pattern. Europium shows a strong positive anomaly in the fluid samples. This europium anomaly indicates high-temperature plagioclase feldspar rock alteration. The chemical signature mirrors ancient volcanic rocks found on land. Scientists use these trace elements to track fluid migration pathways. The Shinkai 6500 deployed specialized titanium syringes for precise sampling. These syringes prevent atmospheric contamination of the pristine deep fluids. Every chemical measurement requires meticulous laboratory calibration and careful handling. The deep ocean pressure keeps the dissolved gases in the vented. Chemicals do not simply vanish into the ocean. They form massive hydrothermal plumes suspended in the water column. These chemical clouds spread laterally along neutral ocean buoyancy horizons. The Chi-ray plume stabilizes roughly 200 meters above the seafloor. Ocean currents carry this chemical signature for hundreds of kilometers. Sensitive sensors on the RV NOR track these deep chemical clouds. Nephelometers measure the light scattered by suspended heavy metal particles. Miniature autonomous underwater vehicles map the chemical plume dispersion patterns. The chemical oxidation of dissolved iron consumes dissolved oxygen locally. This creates a slight oxygen minimum zone around the vents. Methane oxidizing bacteria consume the dissolved gases within the plume. This microbial activity slowly alters the plume chemistry over time. The spatial distribution of chemicals reveals deep ocean current dynamics. The Mid-Atlantic ridge offers a stark chemical contrast globally. Atlantic vents like TAG show completely different fluid evolution pathways. The central Indian ridge fluids interact with different rock types. Indian Ocean basalt contains highly distinct trace mineral geological assemblages. This creates a unique chemical fingerprint in the hydrothermal fluids. The Edmond Field fluids show higher concentrations of dissolved lithium. Lithium levels reach nearly 1 millimole per kilogram at Edmond. This high lithium suggests extensive interaction with altered crustal rocks. Potassium concentrations also differ significantly between the two ocean basins. Kyrae fluids contain about 25 millimoles of dissolved potassium. The Atlantic tag field shows slightly lower dissolved potassium levels. These regional differences highlight the sheer complexity of global vent systems. Each ocean basin hosts a distinctly tailored deep chemical environment. Magnesium behaves uniquely in these high-temperature hydrothermal vent systems. Incoming seawater contains roughly 53 millimoles of dissolved magnesium. The exiting hydrothermal fluids contain absolutely zero dissolved magnesium chemically. The intense deep heat forces all magnesium into the surrounding crust. This process forms magnesium-rich clay minerals like deep chlorite. Sulfate undergoes a similar dramatic removal process during crustal heating. Seawater sulfate precipitates as anhydrite rock within the crustal fractures. Some sulfate reduces chemically into the toxic hydrogen sulfide gas. The complete removal of magnesium and sulfate defines true vent fluids. Scientists use magnesium levels to calculate fluid purity accurately underwater. Any trace of magnesium in a sample indicates seawater contamination. The Shinkai 6500 pilots expertly avoided sampling ambient cold ocean water. Their precise maneuvering ensured perfectly pure chemical fluid samples. The fluid chemistry of the Indian Ocean vents is constantly shifting. Tectonic earthquake activity along the mid-ocean ridge alters fluid pathways. Earthquakes can suddenly change the chemical composition of a vent. A localized deep tremor might expose fresh rock to the fluids. This exposure causes temporary spikes in methane and hydrogen concentrations. Scientists observed such chemical transients during repeated deep mapping expeditions. The RV nor documented slight chemical shifts over several long years. These slow chemical changes affect the biological communities clinging to chimneys. The chemical environment dictates the survival of every deep-sea organism. From the acidic pH to the toxic hydrogen sulfide gas. Each chemical parameter weaves into a highly complex deep-sea tapestry. The central Indian Ridge remains a dark laboratory of extreme chemistry. Its dark waters conceal endless molecular interactions and hidden chemical reactions. The central Indian Ridge hosts incredibly unique biological communities. These hydrothermal ecosystems differ significantly from known Atlantic equivalents. Deep ocean circulation patterns isolate these distinct animal populations completely. Japanese researchers discovered the Kyrae field at 2,460 meters deep. The remotely operated vehicle Kaiko captured the very first biological images. Dense biological assemblages thrive around the towering black smoker chimneys. Temperatures near these clustered organisms often reach 30 degrees. A sharp thermal gradient strictly dictates where these animals survive. The dominant visual feature is a massive, swirling shrimp swarm. Millions of Rimicaris Kyrae shrimp blanket the rocky mineral deposits. This specific shrimp species exists nowhere else on our planet. They gather in astonishing densities of 3,000 per square meter. These blind crustaceans lack traditional eyes for navigating the darkness. They instead possess a specialized dorsal organ to detect thermal. The shrimp constantly jostle for position within the warm fluid flow. They cultivate specialized episymbiotic bacteria beneath their enlarged carapace shells. These microscopic bacteria oxidize hydrogen sulfide from the vent fluids. The shrimp then consume these bacterial colonies for their primary nourishment. Dr. Cindy Van Dover studied these unique feeding behaviors extensively. She noted their movements resemble a synchronized, slow-motion underwater dance. Just below the shrimp swarms lies another fascinating endemic. Scientists classify this remarkable gastropod as Chrysomalon squamiferum in taxonomic records. This snail builds its shell using iron sulfide compounds from seawater. Graphite and pyrite nanoparticles form a metallic armor over its shell. It is the only known animal to utilize iron in this manner. The snail also features thick, metallic scales covering its exposed foot. These iron scales provide essential protection against predatory crab claws. Researchers first collected these metallic snails during a 2001 biologist Anders Wehren formally described the species several years later. The scalefoot snail houses a massive internal gland filled with bacteria. This esophageal gland produces all the necessary energy for the snail. The snail has completely lost its ability to feed normally. Its digestive tract is reduced to a non-functional, tiny vestigial remnant. Population densities of these snails reach 50 individuals per square meter. They cluster tightly together around the cooler. The Alviniconcha snail features a shell covered in thick, dark periostracum. This hairy covering protects the calcium carbonate shell from acidic dissolution. Alviniconcha snails prefer slightly warmer fluids than their metallic neighbors. They form dense mounds near the active fluid discharge channels. Dr. Shana Gaffredi analyzed the internal symbiotic bacteria of these snails. She discovered they host distinct strains of Campylobacteria within their gills. These bacteria process both hydrogen sulfide and dissolved hydrogen. They contribute significantly to the overall biomass of the Kyre field. Biomass measurements here exceed 10 kilograms of wet weight per square meter. This biological density rivals the most productive tropical rainforest ecosystems. Deep-sea mussels also colonize the rocky basalt surrounding the vent chimneys. The species Bathymodialus maricindice dominates the peripheral hydrothermal biological zones. These mussels anchor themselves to the rocks using strong byssal threads. They form extensive beds stretching across the fractured volcanic. Water temperatures in the mussel beds average around 6 degrees Celsius. These bivalves possess dual symbionts within their enlarged gill tissues. They host both sulfide oxidizing and methane oxidizing bacterial strains simultaneously. This dual capacity allows them to survive fluctuating vent fluid compositions. Researchers aboard the RV Pelagia mapped these extensive mussel beds carefully. They utilized high-resolution acoustic sonar to estimate the total population size. The mussel beds provide essential habitat for numerous smaller secondary branchipolliner worms. Actually live inside the mantle cavity of the mussels. They steal small food particles directly from the host mussel gills. Squat lobsters patrol the outer edges of the dense mussel beds. The Munidopsis species uses its long claws to scavenge fallen debris. These blind crustaceans carefully avoid the dangerously hot vent fluid streams. Yeti crabs represent another fascinating crustacean found in this ocean basin. Scientists from the University of Southampton discovered them near the Edmund. They possess dense setae covering their entire ventral abdominal region. These hairy structures farm specialized epibiotic bacteria for the crab. The crabs rhythmically wave their bodies through the nutrient-rich fluid. This continuous movement provides fresh oxygen and sulfides to their bacteria. They use specialized mouthparts to harvest the bacteria from their hairs. Yeti crabs congregate in tight clusters numbering hundreds of individuals. They stack upon each other near the steepest thermal vent gradients. He noted their population density reached an astonishing 600 per square meter. The Edmund vent field lies at a depth of 3,290 meters exactly. This deeper location creates higher pressure environments for the resident fauna. The biological community at Edmund shows subtle differences from the Kyre field. Sea anemones of the genus Marionactis attach to the peripheral basalt rocks. These pale anemones extend long tentacles to capture drifting organic particles. They lack symbiotic bacteria and rely entirely on suspension. The Neolepis barnacles filter tiny microorganisms from the slow ocean currents. Predatory species constantly patrol this rich oasis of deep-sea life. Pythogorid crabs scuttle across the rocks searching for vulnerable prey items. Ostinogria rodriguezensis is the dominant predatory crab in this specific region. They possess powerful claws capable of crushing small snail shells easily. These crabs often hunt the smaller shrimp near the active chimneys. Zooarcid fish slowly swim through the warm waters above. Their slow metabolism allows them to survive in the oxygen-poor environment. The entire ecosystem relies completely on the foundational microbial mats. Extensive bacterial mats cover every available surface near the fluid vents. These mats consist of billions of individual chemosynthetic microbial cells. Epsilon proteobacteria dominate the highest temperature zones near the fluid exits. They thrive in temperatures exceeding 50 degrees Celsius without any difficulty. Gamma proteobacter prefer the slightly cooler regions of the diffuse gentle ocean currents. Cause the bacterial filaments to sway rhythmically. These mats can reach thicknesses of several centimeters in optimal conditions. They trap suspended minerals and create a soft biological substrate layer. Microscopic nematodes burrow continuously through these thick bacterial layers. Copepods graze along the edges of the mats like tiny cattle. The microbial biomass provides the foundational energy for the entire food web. Without these bacteria, the entire vent community would quickly. Researchers mapped this field at a depth of 2,600 meters precisely. Here, the Alvinicontia snails vastly outnumber the scalefoot snail populations. This variation highlights the complex biogeography of the central Indian Ridge. Larval dispersal plays a crucial role in maintaining these isolated populations. Deep ocean currents transport microscopic larvae between the distant vent fields. Many larvae perish in the cold, nutrient-poor abyssal plains between vents. Only a tiny fraction successfully locate a new active hydrothermal. They discovered that shrimp larvae migrate vertically into shallower ocean waters. The shallower waters provide a faster current for long-distance oceanic transport. The larvae eventually descend back to the seafloor to settle down. This complex life cycle ensures the genetic connectivity of the species. The Indian Ocean vent communities represent a biological crossroads of evolution. They share specific taxonomic traits with both Pacific and Atlantic communities. The Rimicaris shrimp demonstrate a clear evolutionary link to Atlantic. This biological mixing makes the Indian Ocean vents incredibly scientifically valuable. Researchers continue to discover new endemic species during every deep dive. A newly identified species of scale worm was recently documented here. The Painaleopalino worm features intricate dorsal scales resembling golden armor plates. These worms scavenge aggressively across the dense mussel bed environments. Another unique discovery includes a specialized species of deep-sea limpet. The Lepidodrylus limpets graze directly on the surface of the mussel. The total biodiversity of these vent fields remains partially undocumented today. Each hydrothermal chimney hosts a slightly different microcommunity of organisms. The chemical composition of the vent fluid drives these microhabitat variations. Higher hydrogen concentrations favor specific bacterial symbionts over other strains. The animals adapt their distribution based on these invisible chemical gradients. Scientific submersibles illuminate this dark world with powerful halogen lights briefly. The robotic arms delicately collect biological samples for surface laboratory. These visual records provide crucial data for marine biological research. The quiet darkness immediately returns once the submersible vehicle departs. The animals resume their continuous struggle for survival in the deep. They remain completely unaware of the sunlit world far above them. Their existence depends entirely on the geological heartbeat of the planet. The central Indian Ridge continues to nurture these remarkable biological oases. Marine virologists also study the invisible viral communities within these. This viral predation helps regulate the overall bacterial population growth naturally. The Pelagia vent field offers another glimpse into this hidden world. It sits at a shallower depth of approximately 2,000 meters. The biological density here appears slightly lower than the Kyray field. However, the exact same dominant species still control the primary habitat. The scalefoot snails at Pelagia display a slightly different shell morphology. Their iron sulfide scales appear somewhat lighter. In the entire vent ecosystem operates in complete darkness without solar energy. Chemosynthesis replaces photosynthesis as the primary driver of biological life here. The Earth itself bleeds essential nutrients directly into the cold ocean. These chemical nutrients sustain a delicate balance of deep marine life. The Indian Ocean vents remain a crucial focal point for conservation. Deep-sea mining proposals threaten these incredibly fragile biological communities directly. Extracting massive sulfide deposits could destroy these unique habitats. It represents the first deep-sea animal protected due to mining threats. Researchers advocate strongly for establishing protected marine sanctuaries around these ridges. Preserving these hydrothermal systems ensures the survival of countless undiscovered species. The mysteries of the deep ocean still hold many scientific surprises. Every new expedition reveals another fascinating layer of biological complexity. The intricate web of life continues to thrive in the abyss. The central Indian Ridge hides a truly unique biological community. This gentle ecosystem thrives at 25 degrees south latitude. It rests at a crushing depth of 2,460 meters. Total darkness blankets the rugged volcanic ocean floor constantly. Here, life does not depend on the distant sun. Instead, it relies on entirely different chemical energy sources. This is the quiet domain of deep ocean chemosynthesis. Superheated water pours from the fractured crust below continually. This fluid reaches temperatures of 360 degrees Celsius. It carries dissolved minerals from deep. Microbes perform the crucial first step in this environment. They act as the primary producers of the ecosystem. These bacteria absorb hydrogen sulfide from the venting fluids. They oxidize the chemicals to create organic carbon molecules. This delicate process replaces photosynthesis in the deep sea. The energy flow begins with these invisible microbial mats. Thick layers of bacteria coat the surrounding basalt rocks. They also float freely within the warm hydrothermal plumes. Billions of microbes provided the Kyre vent field showcases this unique biological structure. Japanese researchers discovered this site using the ROV Kaiko. The discovery occurred during a pivotal expedition in 2000. Kaiko captured the first images of this alien landscape. Scientists noticed a strange blend of different ocean species. The Indian Ocean serves as a massive biological bridge. It connects the Atlantic and Pacific hydrothermal vent populations. This geographic position creates a highly unusual faunal mix. No other ocean ridge displays dense swarms of pale shrimp dominate the Kyre chimneys. Marine biologists officially named this specific species Rimicaris kyrae. These shrimp closely resemble those found in the Atlantic. They gather in thousands around the smoking mineral chimneys. The shrimp do not hunt for food in the darkness. Instead, they farm their own food on their bodies. Specialized gill chambers house thick colonies of symbiotic bacteria. The shrimp gently bathe their gills in the vent fluid. This action feeds the bacteria with another remarkable creature lives near the base of these chimneys. It is the famous scalefoot snail, Chrysomallant squamiferum. This snail possesses a shell made of iron sulfide. It is the only known animal to use iron this way. The snail absorbs toxic metals from the hydrothermal fluids. It safely deposits these metals into its unique armor. Thick, metallic scales cover the fleshy foot of the snail. Like the shrimp, this snail relies entirely on symbiosis. A large internal gland houses billions. Further north lies the massive Edmond hydrothermal vent field. This site sits at 23 degrees south latitude. It is significantly deeper, resting at 3,300 meters down. The water pressure here reaches roughly 330 atmospheres. Temperatures of the venting fluid hit 380 degrees Celsius. Despite the extreme conditions, life flourishes at the Edmond site. However, the biological community here looks slightly different. The ecosystem structure shifts as the ocean depth increases. Different chemical concentrations dictate which species can. At the Edmond field, Alviniconcha snails begin to appear. These large, hairy snails are typically found in the Pacific. Their presence in the Indian Ocean surprised many marine biologists. Dr. Cindy Van Dover studied these unique population distributions. She noted the fascinating overlap of distinct ocean species. Atlantic shrimp and Pacific snails share the exact same ridge. This coexistence proves the Indian Ocean is a transitional zone. The Alviniconcha snails also harbor chemosynthetic bacteria internally. They huddle together in warm crevices near the primary consumers, form the bulk of the vent biomass. Shrimp and snails convert bacterial energy into animal tissue. This process is incredibly efficient in the deep ocean. The sheer density of life here rivals tropical rainforests. Yet, the overall biodiversity remains relatively low by comparison. Only a few highly specialized species can tolerate the toxicity. Hydrogen sulfide is normally lethal to most marine life. These vent creatures have evolved special blood-binding proteins. These proteins safely transport toxic energy flows upward from the consumers to the local predators. Pythagoreid crabs slowly patrol the edges of the vent fields. These pale, blind crabs are the apex predators here. They carefully pick off injured or dying shrimp from the rocks. Their claws are perfectly adapted for crushing snail shells. The crabs move with a slow, deliberate grace in the dark. They avoid the hottest water near the chimney openings. Instead, they wait in the cooler peripheral zones for prey. These crabs represent the secondary small, lethargic zooarcid fish also inhabit the Kyre vent field. These deep-sea eelpouts weave slowly through the shrimp swarms. They occasionally snap at small crustaceans drifting in the current. Their metabolism is incredibly slow due to the cold ambient water. The background ocean temperature remains a chilling 2 degrees Celsius. Further out, white anemones cling to the barren basalt rocks. They act as passive suspension feeders in the ecosystem. Their delicate tentacles catch organic detritus falling from the chimneys. They form a distinct boundary ring. The Kyre field possesses another highly unusual chemical feature. It releases massive amounts of dissolved hydrogen gas. This hydrogen comes from a geological process called serpentinization. Seawater reacts with exposed ultramafic rocks deep beneath the crust. This rare reaction produces hydrogen-rich fluids at the seafloor. Some specialized microbes use this hydrogen instead of sulfide. They oxidize the hydrogen gas to generate cellular energy. This alternative energy pathway adds complexity to the food web. It allows different bacterial strains. Scientists constantly compare the Indian Ocean to the Atlantic. The mid-Atlantic ridge features similar large shrimp swarms. However, the Atlantic vents lack the diverse snail populations. The Indian Ocean hosts a much richer variety of gastropods. The scalefoot snail remains entirely unique to the Indian Ocean. It has never been found in the Atlantic or Pacific. This suggests a localized evolutionary event occurred on this ridge. The central Indian ridge acts as an isolated biological incubator. Species slowly adapt to the comparisons with the East Pacific rise are equally fascinating. Pacific vents are famous for their giant tube worms. These massive riffshell worms dominate the Pacific vent ecosystems. Yet, these giant tube worms are completely absent here. The central Indian ridge lacks these iconic red-tipped creatures. Instead, the dense shrimp and snail clusters fill that niche. This absence puzzles marine biologists studying global dispersal patterns. Dr. John Copley investigated this mystery during a 2011 expedition. He sailed aboard the research vessel RV Sun. The RV Sun expedition also explored the Pelagia vent field. This smaller field sits slightly south of the Kyre site. The Pelagia chimneys are shorter and emit less smoke. Yet, they support a vibrant and uniquely structured food web. Small squat lobsters hide in the narrow cracks of Pelagia. They scavenge for bacterial flakes drifting down from above. The fluid temperatures here hover around 310 degrees Celsius. This slightly cooler environment favors different microbial communities. The bacteria here form long. A single hydrothermal chimney hosts dozens of distinct microhabitats. The temperature drops rapidly just inches from the venting fluid. Water goes from 360 degrees to 2 degrees instantly. This steep thermal gradient creates very specific living zones. Some bacteria thrive only in the boiling, oxygen-free water. Other microbes require the cooler, oxygen-rich ambient seawater. The animals position themselves carefully within these narrow zones. The scalyfoot snail prefers the warmer, highly toxic areas. The anemones must stay in the maintaining this isolated ecosystem requires incredible biological resilience. Active hydrothermal vents are highly unstable geological features. Earthquakes can easily shut off the vital fluid flow. When a vent dies, the entire local community perishes. Therefore, these animals must constantly send offspring to new sites. They release millions of tiny larvae into the deep-sea currents. These microscopic larvae drift blindly through the freezing darkness. They can survive for months in a state of suspended animation. Eventually, a few lucky larvae detect the chemical signature. The deep ocean currents above the central Indian Ridge are complex. They flow in slow, massive gyres across the ocean floor. These currents transport the larvae between distant vent fields. This genetic exchange keeps the isolated populations healthy and strong. Scientists use ROV JSON to sample these drifting biological clouds. They analyze the DNA to trace the origins of the larvae. This research reveals the hidden connections between ocean basins. The Indian Ocean serves as a vital genetic highway. It ensures the survival of chemosynthetic. Despite its harsh appearance, this ecosystem is incredibly fragile. The balance of energy and toxicity is perfectly calibrated. Any slight change in fluid chemistry alters the food web. If the iron levels drop, the scalyfoot snail suffers. If the hydrogen sulfide decreases, the shrimp colonies collapse. The entire biological structure depends on the geological rhythm below. Magma chambers deep in the earth dictate the pace of life. This deep-sea food web operates independently from the surface world. It remains untouched by the changing. Studying these vents helps scientists understand the origins of life. The conditions here mimic the ancient oceans of early Earth. A billion years ago, similar hydrothermal vents covered the planet. The first primitive cells may have evolved in such environments. The bacteria found at the Kyray field possess ancient genetics. They offer a living window into our distant biological past. The energy flow here represents the most primal form of sustenance. Minerals and heat combine to create complex organic matter organically. This elegant chemistry requires no light. The central Indian Ridge continues to vent in the darkness. Its towering chimneys slowly grow taller with each passing century. The shrimp and snails maintain their endless, quiet existence. They harvest the minerals pouring from the fractured oceanic crust. The crabs and fish glide through the warm thermal anomalies. This ecosystem represents a triumph of biological adaptation and survival. It demonstrates the incredible versatility of life on our planet. The deep ocean keeps its secrets under thousands of meters of water. Yet, the rhythm of chemosynthesis beats the scientific exploration of the Indian Ocean requires immense preparation. Research vessels travel thousands of miles to reach these coordinates. The central Indian Ridge remains a highly remote geological frontier. Early oceanographers knew very little about this underwater mountain range. Surface maps showed only rough outlines of the submerged peaks. Detailed investigations finally began in the late 20th century. Scientists suspected hydrothermal activity along these divergent tectonic plates. They needed advanced technology to prove their complex geological theories. The vast water column hid the thermal vents completely. Ship-based sensors slowly scanned the dark ocean depths below. Researchers looked for subtle. The year 2000 marked a massive breakthrough in exploration. The Japanese research vessel Kairei sailed toward the southern ridge. Dr. Jun Hashimoto led this ambitious deep-water scientific mission. His team targeted an area near 25 degrees south latitude. They deployed a tethered robotic vehicle named Kaiko into the abyss. Kaiko descended slowly through the freezing Indian Ocean currents. The vehicle reached a depth of 2,400 meters. Powerful halogen lights illuminated the barren basaltic seafloor. The camera feeds transmitted live video back to the surface ship. Scientists watched the monitors with intense and quiet focus. Massive black smoker chimneys suddenly appeared on the glowing screens. This became the first the Kaiko vehicle carried specialized titanium probes for fluid sampling. Robotic arms carefully inserted the sensors into the venting water. Temperature readings spiked to 360 degrees Celsius. The surrounding seawater remained at a frigid 2 degrees Celsius. This extreme thermal gradient fascinated the observing marine geochemists. They triggered the remote valves on the titanium sample bottles. Superheated fluids rushed into the sterile vacuum of the cylinders. The vehicle also collected fragments of the porous sulfide chimneys. These geological samples contained vital clues about the oceanic crust. Researchers wanted to understand the mineral composition of the vents. The Kairei field proved news of this discovery prompted further international scientific expeditions. In 2001, an American research team organized a voyage. The research vessel Melville departed for the central Indian Ridge. Dr. Cindy Lee Vandover served as the chief scientist. Her team brought an autonomous benthic explorer known as ABE. This untethered robot mapped the seafloor using high-resolution sonar. ABE swam independently above the jagged volcanic terrain. It followed programmed grid patterns to survey the dark ocean floor. The robot detected another massive thermal plume in the dark water. This new anomaly sat 160 kilometers south of Kairei. ABE recorded precise variations. The team named this newly discovered area the Edmund Vent Field. Edmund rested at a much greater depth of 3,000 meters. They deployed the remotely operated vehicle Jason to investigate further. Jason carried high-definition cameras and highly sensitive chemical analyzers. The descent took several hours through the crushing water pressure. Navigating the deep terrain required extreme precision from the pilots. Acoustic transponders on the seafloor helped triangulate the vehicle position. Jason discovered towering chimneys emitting thick clouds of black smoke. The fluid temperatures here reached 380 degrees Celsius. Dr. Robert Vrijenheek directed the biological sampling operations from the ship. The robot used to genetic sequencing preparations began immediately in the ship laboratory. Scientists needed to preserve the biological samples in liquid nitrogen. They worked through the night to process the incoming biological material. These genetic codes revealed connections to Pacific and Atlantic ecosystems. The Indian Ocean served as a biological bridge between the oceans. Later expeditions expanded the search along the northern ridge segments. The Chinese research vessel Dayanghihao arrived in 2005. This mission represented a major global circumnavigation for deep ocean research. They utilized deep-towed optical systems to scan the dark seabed. Cameras snapped thousands of photographs of the passing volcanic rock. Computers analyzed these images. Indian scientists also launched dedicated missions to their namesake ocean. The research vessel Sagar Kanya surveyed the deep tectonic boundaries. They deployed miniature temperature loggers across the spreading ridge axis. These instruments recorded thermal fluctuations over many consecutive months. Understanding the fluid flow rates requires long-term continuous monitoring. Hydrothermal systems naturally change their output over decades of time. Earthquakes along the ridge can suddenly alter the subterranean plumbing. New fractures open while old mineral channels become completely blocked. Scientists drop heavy acoustic releases to anchor their monitoring stations. Glass flotation spheres keep the delicate instrument standing perfectly upright. A simple acoustic command from the German researchers contributed significantly through the Index exploration project. The research vessel Sun mapped the ridge with multi-beam echo sounders. Acoustic pulses bounced off the seafloor to create detailed topographic maps. They deployed the remotely operated vehicle Keel 6000. This powerful robot can operate at depths of 6 kilometers. Its mechanical arms possess incredible strength and fine motor control. Pilots used force feedback joysticks to manipulate delicate deep-sea sensors. They placed chemical analyzers directly into the venting fluid streams. These in-situ measurements prevent data corruption from ambient pressure changes. Bringing samples to the surface often alters their delicate chemical states. Dissolved gases escape. In 2006, Dr. Ken Takai led a microbiology mission. He utilized the Japanese crewed submersible named Shinkai 6500. This titanium sphere carries 2 pilots and 1 observing scientist. The descent to the Kairai field took over 2 hours. Inside the sphere, the ambient temperature dropped as they sank deeper. Condensation formed on the thick acrylic viewing ports of the cabin. Dr. Takai observed the massive chimneys with his own eyes. Human presence in the deep ocean offers a unique spatial perspective. Cameras cannot fully capture the massive scale of these mineral towers. The submersible collected pristine samples of the surrounding vent fluids. They specifically targeted back on the ship. Microbiologists cultured these rare thermophilic bacteria. They recreated the extreme deep-sea conditions inside laboratory incubators. These organisms thrive in temperatures exceeding 100 degrees Celsius. The researchers fed them a steady diet of dissolved hydrogen gas. Studying these microbes helped scientists understand early life on Earth. The Indian Ocean vents provide a perfect analog for ancient oceans. Technological breakthroughs continually improve the quality of deep-sea data. Laser Raman spectrometers now operate perfectly in the freezing water. These lasers identify specific molecules by measuring scattered light patterns. Scientists can instantly detect methane, and French marine institutes also joined the exploration of this region. They brought the sophisticated ROV Victor 6000 to the ridge. This vehicle discovered the Solitaire vent field further to the north. Solitaire features unique mineral structures and entirely different biological ratios. The fluid chemistry here shows a lower concentration of dissolved iron. Researchers carefully documented the sparse biological communities at this site. They deployed sediment traps to catch falling organic particles. These funnel-shaped devices hang silently in the dark water column. They collect the microscopic debris raining down from the surface ocean. Understanding the local carbon cycle requires time-lapse cameras provide another vital tool for long-term vent monitoring. Scientists place these heavy camera systems near active chimney structures. Powerful flashes illuminate the dark seafloor once every few hours. The cameras document the slow movements of deep-sea snails. They record the gradual growth of new mineral deposits over time. Researchers can watch entire biological life cycles unfold in the dark. Navigating these remote underwater mountains requires highly advanced acoustic positioning. Ships use dynamic positioning systems to maintain their exact surface coordinates. Satellite signals link the vessel to precise global positioning networks. Thrusters automatically adjust the ship to counter strong ocean currents. This stability ensures the tethered robots remain safe below. A severed fiber optic cable would mean losing a multi-million-dollar vehicle. The cables transmit massive amounts of scientific data every single second. The Dodo vent field was mapped near 19 degrees south latitude. This specific site exhibited very different hydrothermal fluid signatures. Geochemists measured higher levels of dissolved silica in the venting water. The chimneys here possessed a distinct grayish-white mineral coloration. Scientists used acoustic Doppler current profilers to measure the rising plume. These instruments track the movement of microscopic particles in the water. They calculate the exact velocity and volume of the escaping fluids. This data helps determine the total heat output of the vent field. The Indian Ocean vents release massive amounts of geothermal energy. This heat slowly warms the Pelagia vent field, offered yet another unique geological setting. Expeditions found this site hidden within a deep tectonic depression. The steep basaltic walls made robotic navigation incredibly difficult. Pilots carefully maneuvered the ROVs around the jagged volcanic cliffs. They successfully retrieved fluid samples from the base of the chimneys. These missions generate terabytes of scientific data for future analysis. Laboratory work continues for many years after the ship returns home. The legacy of these scientific expeditions grows with every new voyage. A detailed map of the central Indian Ridge slowly takes shape. We now understand the fundamental chemistry of these deep ocean oases. Future missions will deploy new generations of autonomous underwater gliders. These silent robots will patrol the ridge for months at a time. They will detect the faintest chemical traces in the dark water. The quest for knowledge in the deep Indian Ocean never truly ends. Scientists continue to design better tools for extreme pressure environments. Every sensor and probe brings us closer to understanding our planet. The dark depths still the central Indian Ridge offers a unique geological perspective. We can compare these vents to other global systems. The East Pacific rise spreads at a rapid pace. Pacific vents often form highly active, short-lived chimneys. The Mid-Atlantic ridge spreads at a much slower pace. Atlantic hydrothermal fields remain stable for many millennia. The central Indian Ridge represents an intermediate spreading center. It combines features from both major ocean ridge systems. The Kairai field sits at 25 degrees south latitude. Its longitude is 70 degrees and 2 minutes east. This specific location bridges two vast biological provinces. Deep currents carry larvae from the Pacific Ocean floor. Atlantic species also migrate toward these Indian Ocean coordinates. The Edmund Field lies slightly north of the Kairai. It rests at a depth of 3,300 meters. Fluid temperatures here reach 360 degrees Celsius. Pacific vents typically host giant red tube worms. Atlantic vents are dominated by swarms of blind shrimp. The Indian Ocean vents feature a strange biological mixture. Scalefoot snails thrive alongside specialized anemones and crabs. Biologist Cindy Lee Vandover studied these unique intersections. She noted the evolutionary puzzle presented by this fauna. Genetic markers show a complex history of deep migration. The Indian Ocean acts as a global deep-sea crossroad. Scientists and researchers look to these vents for origin of life theories. The deep ocean floor mimics the conditions of early Earth. A billion years ago, our planet was hostile and toxic. Sunlight could not penetrate the thick, primitive atmospheric haze. Life likely began in the dark, pressurized ocean depths. The Kyre hydrothermal field produces abundant hydrogen gas. Hydrogen is a crucial energy source for primitive cellular metabolism. A chemical process called serpentinization occurs beneath the seafloor. Seawater reacts violently with exposed mantle rock called peridotite. This reaction releases heat, hydrogen, and various organic compounds. Geochemist Michael Russell proposed the alkaline hydrothermal vent theory. He suggested that life emerged within porous mineral chimneys. The tiny mineral compartments acted as the first cell walls. Natural proton gradients provided the necessary energy for early life. The Edmund Field vents fluids rich in iron and sulfur. These elements form iron-sulfur clusters in the surrounding water. Modern biological enzymes still rely on these exact same clusters. Biologist William Martin expanded upon this deep-sea origin model. He traced genetic lineages back to a single ancestral organism. This organism is the last universal common ancestor, or LUCA. LUCA likely thrived in a hot, oxygen-free hydrothermal environment. The Indian Ocean vents provide a perfect modern analog. Scientists collect fluid samples to detect abiotic organic synthesis. They look for amino acids forming without biological intervention. Finding these molecules would prove life can start from rock. Each sample bottle holds clues to our deepest evolutionary. Exploring these remote Indian Ocean habitats presents immense technological challenges. The extreme hydrostatic pressure quickly crushes standard scientific equipment. At 3,000 meters, pressure exceeds 300 atmospheres. Engineering materials must withstand constant, immense physical compression forces. The Japanese submersible Shinkai 6500 frequently visits this ridge. Its titanium pressure sphere protects 3 human occupants from the depths. The research vessel Yokosuka deploys this submarine into the dark waters. Operating crewed submersibles requires meticulous planning and perfect weather conditions. Remotely operated vehicles offer a safer alternative for deep-sea exploration. The ROV Jason has conducted numerous dives along the central Indian Ridge. A long armored tether connects the ROV to the surface ship. This cable transmits high-definition video and receives pilot commands instantly. However, the corrosive hydrothermal fluids pose a constant mechanical threat. Superheated acidic water rapidly degrades exposed metal and synthetic seals. Fine sulfide particles penetrate gears and joints, causing severe friction. Maintenance crews spend hours cleaning the vehicles after every single dive. Complete darkness requires powerful external lighting arrays to illuminate the chimneys. The lights consume massive amounts of electrical power from the ship. Autonomous underwater vehicles map the ridge without a physical tether. The AUV Abyss glides silently above the jagged basalt formations. It uses multibeam sonar to detect unmapped hydrothermal vent plumes. Programming these autonomous robots requires highly complex navigation algorithms. The rugged terrain creates dangerous acoustic shadows and sudden obstacles. Retrieving data from an AUV takes hours of slow surface downloading. The vastness of the mineral wealth of the central Indian Ridge attracts significant economic interest. Hydrothermal fluid continuously deposits valuable metals onto the cold ocean floor. These deposits form massive polymetallic sulfide structures over thousands of years. The chimneys contain high concentrations of copper, zinc, and precious gold. Rare earth elements also accumulate within the surrounding metalliferous sediment layers. Modern electronics and renewable energy technologies rely heavily on these specific elements. Terrestrial mines are slowly depleting their easily accessible high-grade mineral reserves. Industrial mining corporations view the deep seafloor as an untapped resource frontier. The Edmund Field holds thousands of tons of precipitated sulfide minerals. Extracting these resources requires massive robotic crawlers to grind the chimneys. Heavy lift systems would then pump the crushed ore to a surface vessel. Beyond raw metals, the biological resources offer immense pharmaceutical potential. This process is known in the scientific community as marine bioprospecting. Extremophile bacteria possess unique enzymes capable of surviving extreme heat. These resilient enzymes can improve industrial chemical processes and medical diagnostics. Genetic material from vent organisms might hold cures for human diseases. Researchers isolate novel antibiotic compounds from the thick microbial mats. The scalefoot snail produces a unique iron sulfide biological armor. Materials scientists study this shell to design better protective military gear. The commercialization of deep-sea genetics raises complex international. The Kyray field also exhibits unique geological formations rich in silicates. Subsurface fluid channels concentrate valuable trace metals in hidden crustal pockets. Geologists use seismic reflection techniques to estimate the total mineral volume. Acoustic waves penetrate the seafloor to reveal buried sulfide mounds. The true economic value of these hidden deposits remains largely unknown. Extracting them would cause irreversible damage to the fragile benthic ecosystem. Plumes of toxic mining dust could suffocate filter-feeding organisms miles away. Noise pollution from heavy machinery would disrupt marine mammal communication networks. The deep sea operates on an incredibly slow biological time scale. A destroyed hydrothermal vent community might take centuries to fully recover. Some endemic species' live conservation of the Indian Ocean vents requires unprecedented international cooperation. The International Seabed Authority manages all activities beyond national maritime jurisdictions. This organization drafts strict environmental regulations for prospective deep-sea miners. Establishing marine protected areas in the deep ocean is highly complex. Scientists advocate for preservation zones around the most biologically diverse vents. The Kyray and Edmund fields are prime candidates for total protection. Researchers deploy long-term monitoring stations to observe natural environmental baseline conditions. These instruments record temperature fluctuations, fluid chemistry, and local seismic activity. Understanding natural changes is necessary before measuring any human industrial impacts. The deep ocean remains the least protected habitat on Earth. Only a tiny fraction of the seafloor enjoys formal legal sanctuary. Environmental groups petition governments to ban deep seabed mining entirely. They argue that the ecological risks far outweigh the short-term profits. The interconnected nature of ocean currents means localized damage spreads globally. Larval dispersal pathways could be permanently severed by large mining operations. The scalefoot snail was recently declared an officially endangered marine species. This marked the first time a deep-sea animal received this status. Its inclusion on the red list highlights the growing conservation urgency. Protecting the central Indian Ridge preserves a vital piece of natural history. These vents are irreplaceable laboratories for studying the mechanics of the spreading rate of the central Indian Ridge influences its geology. It moves at about 50 mm per year on average. This moderate speed creates deep rift valleys and steep flanking mountains. The Mid-Atlantic Ridge moves at only 25 mm per year. The East Pacific Rise races apart at 100 mm. These tectonic differences dictate the frequency of underwater volcanic eruptions. Indian Ocean vents experience fewer eruptions than their Pacific counterparts. This relative stability allows large, complex chimney structures to mature slowly. The Kairai field features massive sulfide blocks towering over the basalt. The search for life's origins requires pristine, uncontaminated deep-sea samples. Scientists use titanium syringes to draw fluids directly from the vents. These specialized containers maintain the extreme pressure of the deep ocean. Bringing depressurized samples to the surface would destroy fragile organic molecules. The hydrothermal fluids contain dissolved gases essential for primitive metabolic reactions. Carbon dioxide and methane bubble up from the Earth's hot mantle. Microbes use these simple gases to build complex cellular structures. This process is called chemosynthesis, and it operates entirely without sunlight. Navigating the central Indian Ridge requires highly advanced acoustic positioning systems. GPS signals cannot penetrate the deep, dense layers of ocean water. Ships drop acoustic transponders onto the seafloor to create a grid. The ROV pings these transponders to calculate its precise physical location. The changing density of seawater constantly bends and distorts acoustic signals. Pilots must constantly adjust their navigation models to avoid dangerous collisions. The International Seabed Authority holds its meetings in Kingston, Jamaica. Diplomats debate the future of the central Indian Ridge mineral blocks. Several nations have already secured preliminary exploration contracts for this region. These contracts allow mapping and sampling, but not commercial. The Indian Ocean vents hold hidden connections to global climate. These deep fissures release enormous amounts of chemical energy constantly. Microbes harness this energy to build complex organic molecules efficiently. This process is known in biology as deep chemosynthesis. It captures carbon dioxide dissolved in the deep ocean water. Billions of microscopic organisms trap this carbon every single day. They lock away carbon deep beneath the ocean's surface permanently. When these organisms die, their remains sink into the sediment. The seafloor mud becomes a massive underwater carbon storage sink. This natural sequestration helps regulate global atmospheric chemistry over time. Scientists are just beginning to measure this massive carbon vault. Dr. Cindy Van Dover studies these carbon pathways very carefully. She measures carbon isotopes near the Kairai hydrothermal vent field. This field sits at coordinates 25 degrees south latitude. It lies at exactly 70 degrees east longitude without deviation. The depth here measures 2,420 meters. The vent fluid temperatures reach 360 degrees Celsius. The surrounding water remains near 2 degrees Celsius constantly today. This extreme temperature gradient drives intense marine biological productivity locally. The biological pump here operates without any natural sunlight entirely. Hydrothermal systems play an unquantified role in this chemical absorption. We must map these carbon pathways to understand our planet. The central Indian ridge hides many more undiscovered vent fields. Each new field adds to the global carbon sequestration total. The dark ocean acts as a silent guardian of stability. Carbon atoms cycle through these deep ecosystems very slowly indeed. They remain trapped in the abyssal mud for thousands. Heat from the Earth's mantle also influences ocean circulation patterns. The central Indian ridge releases massive amounts of thermal energy. Superheated water billows into the freezing abyssal plains continuously today. This thermal input alters local water density very significantly indeed. Warmer water rises and mixes with the cold deep currents. Dr. Edward Baker studies these deep ocean thermal plumes extensively. He tracks how heat dissipates across the Indian Ocean basin. The rising plumes create massive underwater weather systems far below. These deep sea storms stir vital nutrients from the bottom. The mixing process affects global thermohaline circulation patterns very deeply. This circulation acts as a giant planetary conveyor belt system. It distributes ocean heat from the equator to the poles. Vent systems provide localized heating stations along the mid-ocean ridge. They inject heavy metals and trace elements into the currents. Iron from the Edmund vent field travels for thousands of miles. This particular field is located at 27 degrees south. Its exact longitude is 65 degrees east without fail. The depth here plunges to 3,290 meters. Iron acts as a crucial fertilizer for surface ocean phytoplankton. These surface algae produce half the oxygen we breathe daily. The deep vents secretly nourish the sunlit surface waters above. The planetary ocean is completely interconnected in this beautiful way. Thermal energy from the core sustains life above the waves. Oceanographers use physical models to trace these hidden thermal currents. They measure temperature anomalies down to 1/1000th of a degree. The Indian Ocean remains the least sampled major ocean basin. Its thermal contributions are still being actively. Many scientific questions about these vents remain completely unanswered today. We do not know how vent larvae cross vast ocean trenches. Their migration patterns across the Indian Ocean are still mysterious. Genetic connectivity between distant vent fields puzzles marine biologists constantly. We need more data to map these deep biological highways. New technology makes this future research possible and incredibly safe. Autonomous underwater vehicles now patrol the central Indian Ridge autonomously. The AUV Sentry maps the seafloor using high-resolution multibeam sonar. It glides silently 20 meters above the jagged basalt rocks. Sentry creates topographical maps with incredible precision and perfect clarity. These maps reveal tiny fissures venting warm mineral water constantly. Remotely operated vehicles follow up on these detailed sonar maps. The ROV Jason dives deep to collect physical geological samples. It is equipped with highly advanced titanium manipulator arms today. High-definition cameras capture the alien landscape in perfect clarity. Jason carries sophisticated in situ mass spectrometers on its frame. These instruments analyze vent fluid chemistry in real time underwater. They detect rare isotopes and dissolved gases almost instantly now. This technology eliminates the need to bring unstable fluids up. Pressure changes often ruin delicate chemical samples during the ascent. Real-time analysis preserves the integrity of the scientific data. Scientists sit in control rooms thousands of miles away safely. They watch live feeds transmitted via high-speed satellite connections. The deep sea is finally becoming accessible to global researchers. Engineering breakthroughs continue to push the boundaries of deep exploration. Several major expeditions are planned for the coming decade ahead. Dr. Kentakai leads a team investigating extreme marine microbiology. His upcoming mission targets the northern central Indian Ridge specifically. They seek hyperthermophilic archaea living inside the dark chimney walls. These microscopic microbes might hold clues to the origins of life. The expedition will utilize the deep submergence vehicle named Alvin. Alvin has been upgraded recently to reach even greater ocean depths. The new titanium personnel sphere can withstand crushing abyssal pressures. Scientists will spend 9 hours sealed inside the tiny sphere. They will observe the hydrothermal ecosystems with their own eyes. Another expedition focuses on the geological evolution of the ridge. Geologists want to understand the slow-spreading tectonic plates better. They will deploy a network of ocean bottom seismometers soon. These sensitive devices record micro-earthquakes beneath the ocean crust constantly. Magma movement generates faint seismic tremors constantly in the dark. Tracking these tremors helps predict where new vents will form. The Indian Ocean ridge spreads at a very intermediate rate. This specific speed creates unique hydrothermal chimney structures over time. Researchers hope to find dormant chimneys rich in rare minerals. Dr. Sylvia Earle advocates for the non-invasive study of these areas. She emphasizes the vital need for baseline ecological data collection. We must understand these habitats before human interference occurs there. The future of deep-sea research relies on international collaboration. Ships from multiple nations share data and resources freely today. This open science approach accelerates our understanding of the abyss. The wonder of deep-sea exploration humbles the human mind. We have mapped more of the moon than the deep sea floor. The central Indian Ridge remains a true frontier of pure discovery. Every expedition returns with species entirely new to modern science. We find snails with iron armor and blind pale crabs. These creatures evolved in complete isolation for millions of years. They thrive in toxic waters that would kill surface life. Their resilience demonstrates the sheer adaptability of biology on Earth. We must protect these fragile deep ocean ecosystems from harm. The threat of deep-sea mining looms over hydrothermal vents. Mining companies want to harvest the massive copper and gold deposits. These metal sulfides formed slowly over thousands of years of venting. Mining would destroy the delicate biological communities almost instantly forever. Plumes of disturbed sediment would smother the filter-feeding organisms. The noise pollution would disrupt the deep ocean acoustic environment. Conservationists argue strongly for the creation of marine protected areas. The International Seabed Authority regulates these remote international waters currently. Scientists advise strict environmental frameworks for any future commercial activities. The Kairai and Edmund fields deserve permanent ecological protection immediately. Their scientific value far outweighs the price of their rare minerals. We hold a profound responsibility to preserve this hidden world. Future generations deserve to study these untouched alien landscapes safely. The deep ocean is a planetary heritage that belongs to everyone. Protecting the deep sea ensures the health of the entire ocean. The interconnected nature of water. I invite you to appreciate these hidden deep sea worlds. Imagine the silent darkness of the vast abyssal plains tonight. Picture the towering mineral chimneys venting black smoke quietly upwards. Visualize the shimmering heat waves distorting the freezing ocean water. Think of the ghostly white crabs moving slowly over basalt rocks. These scenes exist right now at the bottom of the world. They continue their ancient rhythms far away from the sun. The deep ocean operates on a completely different scale of time. Centuries pass like seconds in the eternal midnight zone below. Let the calm persistence of this ecosystem soothe your tired mind. The steady flow of geothermal energy is a comforting constant. The earth breathes slowly through these deep hydrothermal fissures always. The ocean currents gently sweep across the dark rocky valleys. Life finds a way to flourish in the harshest possible conditions. This biological resilience brings a sense of deep peacefulness tonight. The mysteries of the Indian Ocean vents will wait for tomorrow. The scientists have turned off their remote cameras for now. The research vessels drift quietly under a blanket of stars. The deep sea returns to its natural undisturbed silence completely. The heavy water pressure holds everything in a gentle embrace. It is time to let go of the waking world entirely. Allow your thoughts to sink down into the calm abyss. The ocean will continue its slow rotation through the night. The deep vents will keep warming the freezing bottom waters. Rest your